So here is episode 3 of our Odyssey of Thermodynamics, in which we're going to talk about standard molar entropies and how using them is an application of the third law of thermodynamics. And so our goal here is to calculate delta S for a chemical reaction, and you could follow along about this in section 16.3 in open sex chemistry. So the third law of thermodynamics tells us that the entropy of a perfectly ordered crystalline substance at 0 Kelvin, absolute zero, is 0. So the idea here is that at absolute zero, molecular motion stops, everything is perfectly ordered, the entropy of everything at absolute zero is 0. So, if we could determine the entropy of something relative to absolute zero, then that would be the standard entropy for that stuff. And so we can tabulate a whole bunch of molar entropies, and you can find them in your textbook in Appendix G. And if we know those, then we can calculate the difference in entropy between the products and the reactants, the same way you used heats of formation to calculate delta H of a reaction in Chem 131. This works because the entropy change for a reaction is a state function, meaning it only depends on the beginning and the ending. What are the reactants? What are the products? Not on the mechanism to get there. We can calculate the delta S for a reaction using values from Appendix G, like in this one. Here in lightning storms, oxygen is converted into ozone, and we can calculate delta S for this reaction. So we said that delta S for a reaction equals the sum of the standard molar entropies for the products minus the sum of standard molar entropies for the reactants. Okay, so getting started on that, here our products are 2 molecules of ozone, and so we can use the standard molar entropy value for ozone, 238.9 joules per mole times Kelvin. Okay, so that pretty much takes care of our products, minus 3 moles of the value for oxygen, 205.2 joules per mole times Kelvin. And if you do the arithmetic on that, you should get that delta S for this reaction is negative 137.4 joules per mole times Kelvin. Okay, so that seems simple enough. Some things to notice here. First, the units on delta H and delta G are both kilojoules per mole. The units on delta S are joules per mole times Kelvin. So entropy values tend to be smaller than the enthalpy values. Also, the delta H for an element like O2 is 0, but that's not true for the entropy values. So entropy values for elements still have values. Finally, we note that delta S of this system is negative. So delta S decreases. So entropy is decreasing. This is becoming more ordered, which is what we predicted in a previous video when we noticed that we're getting fewer independent particles. Delta S is negative. However, this reaction still happens because it must be that the delta S of the surroundings increases. So we can see how even just a simple problem like this brings together several of the ideas that we've been talking about.